Okay, welcome. DEFCON 22. Seahawks. So, I came up with some stuff between when I submitted my slides and the conference. So there's a little bit of a deviation here from what you guys have, but I've got a really awesome tool, and I was like, you know, I'm not going to sit back and not release it. So I'm still going to sandwich in the page table shellcode stuff, which really isn't new. I did do that at CanSec West, you know, but I do have some new stuff. I held it back just for you guys, DEFCON 22 exclusive on finding out what's really running on your system. Essentially, we're going to be killing the rootkit. So, any rootkit, I believe, we're going to be able to handle in the future quite decisively. I believe that we have a defensive mode, defensive exploit that you can now use to actively find any attacker in your infrastructure in a very high assurance way. Specifically, the tool that that's on the CD, and then I've got an updated version you can download in the source code as well, whatever. And I re-implemented it in .NET so you can run it in Linux or Mono and all that stuff. Is designed around solving the DCOM type rootkit problem, direct kernel object modification. There was some work earlier on 32-bit similar to this, and then the papers, you know, you can read my slides. There's some references. Just follow the slides, follow the links in the slides. You'll see the references to the 32-bit stuff. But those authors kind of left it a little bit short mode. You know, we're going long. The thing about the 64-bit long mode is now we've got so many more bits we can check. We've got so many more places to identify that if you mess with the bits that we're checking, the system just won't run. You'll get a blue screen, you'll get a crash, you'll get a reboot, whatever. So it's based on properties of the MMU, the virtual management system, and I just wanted to kind of throw that up there so I get you guys engaged. And then I'm going to just briefly talk about the long road to this discovery. So Barnaby Jack, just give him a quick toast here. Forever in our hearts and minds. You know, he would always talk about, or he would talk about, it's about the journey, not the destination. So, you know, with that, I'll have a little bit of the journey here. 13 years ago, I was here at DEF CON. I did ADM mutate. I guess I invented or first released a toolkit for polymorphic shellcode, and then like Spoonman put it into Metasploit, and that's probably the version all you guys are running. But so that was 13 years ago, and you know, the more things change, you know, of course, the more they stay the same. You know, and a lot of these attacks get recycled and brought back. And you know, when I was before I made the discovery on this rootkit detection stuff, and you'll see how that links in with the page table stuff. You know, I thought about even just like doing a new patch for ADM mutate. I was like, hey, 13 years later, I still get the same code I'm talking about. You know, I thought that'd be a little bit funny. But you know, I just wanted something a lot more practical. So. What you guys have now on the CD, I'd love to get some feedback on what your experiences are with this detection technique. And it's definitely a million times more practical than just another attack, just another encoder, just another thingy. You know, an attack is hard and stressful, you know, and people get a lot of kudos for their attacks. And but you know, it all ends up, it's fun. You know, exploiting stuff is definitely fun, and getting that shellcode and getting those root shells and you know, whatever. I mean, it's fun until it's scary. I guess that should have been the last part. Scary, fun, scary. And defense is just a hard stress. That's kind of You know, that's the hard part of defense. And I'm going to try and energize you guys and try and change some of, you know, the way we're kind of thinking about defense. You know, everyone's like, yeah, attacking for fun and profit. I don't think I've ever seen a defense for profit or defense for fun. I've never one talk. Defending my network for fun. What? Really? So, you know, it's obviously the quarterback. Usually gets the headlines. You know, he's making the points. The defense just grinds it out. So, and then, you know, I got this a couple times in here. Just say, let's hear it for the D.
Defense.
Defense.
I lost my voice, sorry.
So.
Fence.
When I say D, she's going to yell fence. Help her out, though. She lost her voice. So.
I lost my voice.
So the idea here is that the tool that I've given you on the CD, or if you want to download the .NET version, which is a slightly enhanced check, it's got 2 different modes instead of the 1 mode check on the CD. Less bit checking and a little bit of logic. Anyway, sort of a defensive exploit. You know, anyone that's been exploited, anyone that's been hacked, you know, sucks getting exploited. Some things that you can do, though, on the defensive side is, you know, you have this historical knowledge and you have an ability to maybe post-process some of these events in, you know, the future, right? Storage is cheap. You know, I'm going to keep my memory dumps around from any incident forever because, you know, maybe there's something I missed. I'm really kind of fanatical about that. It's like, hey, did I miss something? You know, when I do like a forensic or when I look at the memory, the physical memory of a machine, it's like, okay, how do I know I've looked at everything? Did I miss something? I'm always checking myself. You know, I always like to say I'm like one of the worst programmers ever. And that makes me a good code auditor because I've got 0 assumptions about any function call. Like I'm like, you know, like checking man pages, like every line, no problem. So what we've got today is the death of DCOM, which is the direct kernel object modification stuff. Process hiding is dead. Anyone doing process hiding rootkits? That's like, you know, they might as well just be like a wrapper or something else, like easily detectable, I don't know. But that technique is effectively dead now. There's no hiding from it. I'm going to digress a little bit. Also 13 years ago, there was like this insane bash assembler thing. Kind of blows my mind, right? Like what goes on. This guy wrote like an assembler in bash, and you know, so you just think about things. People have been kind of doing this stunt hacking, these stunt tricks for a while. And that was kind of my talk. It was like going to be like this stunty thing with page tables, and then, you know. So anyway, that's probably a little bit why I'm cutting it a little short. I didn't want to be too hackneyed and too just like another stunt. You know, I'm giving you something real. This is something super real. Okay, we're gonna find.
Go, babe.
We're gonna find out as best as possible all possible code running on a machine. There will be no code running that we don't know about. There's ways to inject DLLs and things like this, but that sort of attack is handled by integrity checking, hash checking pretty easily. So I don't want to really spend a whole lot of time on like, hey, this is an integrity checking thing as well, blah, blah, blah. You know, hash checking is kind of like a thing that everyone's really accustomed to on files. It's also possible in memory. So the other thing I wanted to talk about is procedurally, we can devise a system that resists attack, resists backdoors. I noticed, I went to the EFI BIOS talks earlier, and I know the MITRE guys and the Intel guys are all brilliant, awesome work, but practically, if you're an administrator on my host, you know, I mean, it's game over. So I'm not really, like, at that point, I don't believe an attacker's typically going to be escaping the guest on me. You know, if you're using a VM, a cloud, some kind of virtual hypervisor, even something, maybe with a more weaker track record, like, you know, I don't want to call out VirtualBox, but I know that it sometimes crashes more than other VMs. Even that, like, you know, I'm probably not even a great enough target to waste a VirtualBox exploit on, right? So if we use the hypervisor, if we use these systems, we can establish a number of things, and I'll talk about device verifiability, verifying the virtual devices, and all this other stuff as well. And that's why the BIOS EFI stuff is kind of cool. It's not really applicable, I don't think, in a lot of real-world cases, unless you're like living free and wild, bare metal, you know, bare naked bare metal. I don't know. There's 3 pillars here: structural analysis, physical memory traversal, and integrity checking. We need to analyze memory from the physical memory side because I don't want to deal with IDTLB issues, you know, being trapped by like another thread in the kernel, being evaded on, dumping memory. So dumping memory and analyzing physical memory from a VM snapshot is vastly simplified, you know, unless you're going to do a cryo dump of your RAM or something crazy like that. So here are the practical concepts again. The weird machine attacks are awesome. I mean, finding the hidden machine in a custom application, or, you know, code data intermixed in like a font, and that somehow triggers the GPU to do some kind of pixel shading to like anti-alias your frickin' Retina display, and then, you know, that somehow enables that code to like inject into some other memory and yada yada. Yeah, I mean, like, the more esoteric, the more eclectic those attacks, hey, that's awesome, right? That's like the cool stuff. But in the real world, you know, procedurally, we want to adapt the home field advantage to use defensively this structure. I mean, I've been using a hypervisor for like 10 years, right? I don't know. I mean, everyone else, you know, probably the same. So games in the fault handler don't work on VMs, right? The snapshot's going to collect everything, right? If it did work, then the VM, like, period, wouldn't even function. So you know that, like, you're not going to have that shadow walker issue. The BIOS firmware EFI stuff doesn't work either. A lot of VMs don't even support SMM. People are talking about SMM like it's something that still goes on. Well, you know what? There's a lot of hypervisors you can't even get into SMM from the guest. So, you know, you're going to need that VM escape, right? I think that's something that people forget. Like, oh wait, oh yeah, that's after I escape the VM. Well, you know, I'm not the DoD, and you're not China probably, and you're not, you know, wasting that exploit on me. Maybe those guys do, but. Another couple cool properties about this thing that you'll see is that nested page tables, it's not really an issue either. Things like that. So the page table shellcode stuff was, you know, something devised to work on just evolving our understanding of systems and go, okay, this is cool. I can kind of implant memory up until Windows 7 by just, it's sort of a complicated thing, but I'm just going to gloss over it really quick as well. But the motivation was to help understand physical memory systems. So until Windows 7, or after Windows 7, this got fixed. So none of the page table shellcode stuff worked anymore, and I was kind of like de-incentivized to work on like a information disclosure on how to make it better, how to make it weaponized, how to make it like awesomer. If you want to look at this other reference here, the page fault weird machine instructions and instruction-less computation, that's such a mind-melting paper. I mean, they found a way between the interaction of the page fault handler and mapping the TSS and the GDT and doing this crazy faulting. So the faulting itself in the CPU, that would normally be like bringing pages in and dealing with invalid instructions and these sorts of things, that interaction actually read and wrote memory. So all you need is the primitive to read and write memory, and you can kind of coerce that into a weird machine. And they wrote a little compiler for it. It's pretty amazing stuff. Here's an explanation on what the virtual address space looks like on x64. I took this off of Code Machine, also pretty interesting site with lots of other low-level stuff. We can see here that obviously Microsoft has done pretty good. The second row here, you can see that the PTE space is now non-executable. Hyperspace is now non-executable. Microsoft has been doing a good job at reducing the surface area of like what's executable in kernel space. Other people talk about sign drivers, and Joanna had that one attack where she like injected code into the hibernation file and things like that. That was really awesome. They've been working on reducing this stuff. So again, they did patch this stuff. One interesting thing I want you to look at on this slide is look at that left-hand column, that start column there. Those addresses aren't just random. Some of those ranges, what that correlates to is entries in the root global page table, and they can mark security at that root level to kind of adjust the permissions in the entire address space. Here's the actual page table shellcode weird machine. Win7 and earlier, we can actually emit shellcode or emit code into the kernel on Windows 7 and earlier. So I know I love when I was not going to upgrade to Windows 8. I don't know anyone else. Like I was like, I'll wait for 9. But I'm telling you, they did a lot of security. Windows 8's a lot better in the kernel. There's a lot of really interesting things they did. 8.1, they brought back the start menu, so it's like, oh, great. By just doing a virtual alloc in user space, so not as an administrator, an unprivileged user, remote user, even a remote user, if I'm interacting with a service, on like a web server, when I send a request to that server, when it allocates memory to receive that allocation emits executable information into the kernel space. So, what that means is like, I can do a ROP right through that. I can get code into the kernel by just reserving memory, which is pretty powerful, which is pretty interesting. Those E's there, that means that's executable. And then, it wasn't bounded by the amount of physical memory. Just by reserving the space, you would have that area as well. This number here on the left, if anyone knows what that number is, feel free to yell it out. You can't see? Oh, sorry. I assumed people had the slides and stuff. I'll explain later. So again, it's dead, frowny face, or indifferent emote face. If you do want to kind of look at how the kernel in Windows 8 interprets exceptions and KI page fault and how the page fault handler, the internals of it work, feel free to step through it. In this particular stack trace, I was actually pretty perplexed for a while why, if it was patched, I wasn't getting a straight abort exception. This is actually, I guess, a DOS. It'll spin a thread to infinity. And again, so I didn't really, I spent some time kind of wrestling with, okay, I'm going to do this as like a ADM mutate update. They released this .NET compiler thing. Maybe I'll do a compiler. And I was like, maybe I'll do it as a bash script. And I was like, it's really hard to deal with those nulls in bash. And No. So what I did find along the lines was this upcoming technique, and I'll show you in a second on the build up to it. This is going to be the build up. This is going to be the longest build up to one line of code you ever saw. This is one line. This whole technique is one line. It's a big one line, but you know. Instead of doing another attack, instead of trying to be like, just this is how cool my hacking is, this is how cool my stunts are, I'm going to give you a defensive exploit. I'm going to obsolete process hiding. Anyone that does forensics, anyone that does any kind of incident issue, you know, dealing with hidden processes, dealing with this APT threat or whatever you want to call it, is kind of a pain. And now, like after this talk, you can qualitatively say, like, absolutely, you fucking found everything. I did look at everything. There's no hidden process, or maybe there is something new. And no rootkit is safe that I know of at this point. Especially, I mean, and again, in a hypervisor. If you're dealing bare metal, you know, maybe you're a masochist. I don't know. Let's hear it for the D.
Fence. Come on, everybody. I have no voice now. I'm out here.
So there is a sign code example, AMD64. I'm going to be porting it to other architectures soon. The only reason it doesn't work on all architectures immediately is because a property that I'm detecting is something to do with the MMU, and on different operating systems it's in a different offset. But if you guys, if anyone is a harsh kernel debugger with like OS X or Linux or FreeBSD, and you know you want to help me like with that foo, that'd be great. And we're definitely closing the door on the conference today. We're closing the door on the rootkit, and you know, keep your interesting memory dumps around so that you know sometime in the future you can deal with them. And these are some issues again. You know, sometimes I personally feel like I recap stuff too much. Maybe that's because it's like, oh, I know this, and like obviously I wrote these slides. I'm like, dang, did I put the same stuff 3 times in here? But dumping memory is really a pain physically. Please use a hypervisor. Please. I'm not really a super fan of Docker unless it's used in a hypervisor type deployment. You know, zones or whatever, that's not really the most efficient possible thing around. But several different ways to detect hidden processes have been proposed in the past.
Are you guys the ones with the shots, or where are the shots? I was told if I came up here, I'd get some shots.
Wait a minute. Raise your hand if you're a first-time speaker at DEF CON.
No, he's not. He spoke 13 years ago.
Oh. Raise your hand if you're a first-time speaker at DEF CON like 15 years ago. All right.
What does that mean?
Allison gets a shot too.
I was.
All right.
She's brave.
Yay.
So dumping memory is a pain.
Thank you.
Oh no.
Oh no. Sorry.
Spill in aisle 3. Spill in aisle 3.
Oh, Brown.
What? I hope not.
Scanning can be slow and it's a pain. The technique I have is single pass. A lot of other techniques along this line are kind of multi-pass. Multi-pass is like, you know, traversing the memory multiple times. Linked list pointer traversal is easily confused, but it is also super fast. I'm going to back up again and say, like, what is a process?
Don't forget. Step away. What's a process? Holy shit. I guess we're in DEF CON 101. Anyway, no. Hey, listen, it is really hard to get accepted to DEF CON. You've done it once. I'm sorry, back up. You're one of the guys that's been here so long, you've gone back to 0. So, you missed your shot 15 years ago.
Thank you.
How about some love?
Thank you. Cheers.
If you want to take the garbage.
It definitely is an honor and a privilege, and thank you very much for having me. And that's especially why I wanted to bring you guys something fresh and something new and not just another stunt hack.
And by the way, if after 15 years you still don't know what a process is,
well, the reason I put this up, it'll become clear in one slide. A lot of people talk about a process as a thread container, right? But a process is also an address space configuration. They share a common address space, and that's why we got to lock and do things like that. So they're a container for threads. It is kind of difficult to know if you have all the processes, especially if someone's doing this decomp thing and unlinking pointers and whatever else. Process detection for a lot of guys kind of boiled down to these techniques here that volatility has, and which are great. These are great techniques. Volatility is an awesome tool. People should be using it, especially in forensic type situations. The only caveat here is these are logical identifiers. This is a linked list. These are operating system constructs. I mean, so then we're in this cat and mouse game that we're always in, right? Attack, defense. Oh, I found this other table, process thing, K thread, G thread. I don't even know, right? And this is what Takahiro, pardon me if I had butchered your name. Never met the guy in person, just online. And he talked at Black Hat 2012, and he recently did a post, April 2014, about abort factors. So when you're analyzing memory and trying to find out like what's in there, you know, there's these little kajiggy things like flipping a bit here, flipping a bit there in these advanced sort of low-level areas, debug data header 64 thing, where, you know, I think with just like one bit, this guy like crippled all this software. Mandiant, HB Gary, volatility, which are good to use as well, but, you know, can be crippled by this guy's technique, which is a little bit unfortunate. Again, to fully wrap it up before I go on, I wanted to make sure I did the appropriate thing and cited as many people as possible that had led up to this. And the prior work before me, PMO dump, that's the 32-bit one. It's great and everything, but, you know, 32 bits, we just don't have the assurance level that we do on 64. So please go to 64, use a hypervisor, high assurance, you found everything. This technique that I'm going to be showing here in one more slide, the integrity of it, how easy is it to attack this thing? Well, you know, can I make it non-abortable? Yes, I can. The current check is really good, and I would appreciate anybody coming to me with some updates or everything else. This is a quickie to just show you what a PFN is. A PFN is a page frame number. This is like a physical address in the memory dump. Virtual addresses are those bigger numbers usually, but a PFN is what the hardware specifically looks at when it's like number 1 is the first 4K, number 2 is the next 4K. And then here's a slide from Microsoft where it almost shows everything. Essentially what the detection technique I have is based on self-mapping page tables. This CR3 register is the register in your computer that when you switch processes, this register changes and gives you a new address space. And this is what actually gives you the process isolation. Okay? So at the root level, CR3 pointer. And then we've got these other pointers that are kind of like, you see this one kind of pointing back to itself. So that's really handy. It's pointing back to itself in a way that we're going to be able to leverage that to identify any point in time where we can find a page table. And because each process has a page table, inherently we're going to find every process by detecting every page table. It doesn't matter if it's a kernel process, so there could be 2 supervisor processes or something like that, something super weird like a weirdo patched out kernel. That's possible. But definitely, you know, we'll find everything. As well, if you want, any of the Linux guys out here, You know, if you want to help me evolve this technique for Linux or something like that, here's a huge paper on or discussion about the self-map trick in Linux on IOACTIVE no less. So it is cross-platform, cross-architecture, process detection. And this quote here kind of goes down the line of like, okay, the kernel developers really wanted this flexibility when they're dealing with managing memory, right? Having this pointer in there really makes it flexible for them in leveraging, you know, memory allocations and dealing with processors or whatever. So the great thing about it is that it exists for all processes. If you know WinDebug or some other debugger, and you at the you know, doing your kernel debugging, you can go exclamation process 00. This gives you these registers, these CR3 base registers, the page table base directory pointer, whatever you want to call it. It's a really long thing to say all the time. CR3 is a lot shorter. So exclamation DQ is like the physical memory dump. So DQ is dump quad word, but exclamation DQ is dump physical quad word. What we're going to see here is when you do that at the base register for CR3, okay, this is going to be the very first quad word. So null is always going to be mapped, right? Because null needs to be mapped in the virtual memory system, because if it's not, you're not going to appropriately be able to handle like null violations and things like that, right? So that's always going to be there. So there's no plus here. This is the magic number here, F68. So for Windows at least. At this address, which is the base CR3 page table, page directory base pointer, DQ on that, F68, the response is here. What we see. The blue bits here are the bits that are options bits. You can see there's quite a number of them. This middle section of blue bits, this is 32 bits on its own. So you can see this check is very high assurance, essentially. You know, at least double the 32-bit one. The current PFN was found at this offset in physical memory. So just by looking at each 4K by itself at this offset, checking a very few amount of bits. In this case here, it looks like I'm checking a lot of bits. This is, if you do the download, this is the mode 2. Mode 1 only checks 1 bit. So, you know, I'd like to see you attack that. I would like to see someone attack it. But so based on the fact that I can identify the current PFN by looking at physical memory, I can identify all page tables for every process. So PFN for the win. Defensive exploit. Let's hear it for the D.
Feds! Come on, guys. Thank you. Rootkit is dead.
Dead rootkits.
Dead.
Everywhere. So again, it's a more powerful check. A valid PFN is going to be bounded by the constraints of the system physical memory. So this middle bit here, you know, you're going to have a lot of nulls in there unless you've got like terabytes and terabytes of memory and stuff. So those are additional bits we can check because I know how big the input is that I'm looking at, and I know other properties like it's always going to be incrementing and things like that. If you try to attack it, you know, we could do some additional checking. I'd love to see someone come up with an attack. I'll do additional checking. If you want to do attacks, you go exclamation or bang ED at that same physical address. So there's no EQ. You can't edit a quad word for some reason physically. You can dump a quad word, you can't edit it. So, but if you want to play with modifying the page table entries on a kernel debugger, you go bang EQ ED, that same offset from, you know, F68, and then play with those bits and see if you can actually run your system without a BSOD. For me, the system BSODs every time. So that's another helper to your assurance level that you know, you're doing good and everything like that. Here's the implementation of the code. And it's also, it's on the CD and everything like that. The managed version, it's online. You can download it. This is the one line right here. Checking in the middle. Pardon me? You can't see? Just browse to it on your phone or something. I don't know. I'm running short on time. So here's a couple of the cool properties. This is on a vmem. So this is me dumping on a vmem. So this is also format agnostic. So unless you've got some kind of like extents-based memory dump, like some virtual memory system might have, which would be an issue. Here, so VMware it's not an issue. .dmp it's not an issue. What we're going to see here is detected values. And then this diff thing is also really important because it allows us to do something very important. It allows us to detect memory runs. A memory run is like a gap in memory. So the hypervisor establishes these runs so that physical like PCI cards and things like this have their marked areas of memory which aren't actually in the physical memory, they're in that card space or whatever. So we can see here this jump, diff, jump, and then we can round up and round down these other values and we can automatically get the memory gaps. Again, Takahiro has a blog post on pains in the butt he had with finding memory runs, and I'm like, well, shit, now you can use this, and we're all good. Another interesting property of this is you can actually detect processes in guest memory in a VM guest from a host dump. If you really wanted to get really like super awesome with this, you could actually look at this header file for VirtualBox and this page pool thing, and this is what you're going to look at. Essentially, this is dumping a memory dump from a cloud server. It's a this system has 64 gigs, and these diff values you can see are aligned. The first three are aligned. I don't know if you can't see them, then I'm sorry. You gotta pull up the slides on your phone or something. And then we see the skew here because a VM doesn't necessarily, it's allocating memory off the heap on the host. It's not doing it physically, right? So these diffs start to skew, and that's where you're going to have to use that mminternal.h to like demux the offsets and things like this, and it's going to have other structs in there that handle pointers and whatever. And you can see this 187 here. Scream 187 to a motherfucking god.
What?
So 187, I don't know. It's always like the fucking physical page frame number for kernels. Yeah. For some reason, 187 is like always like the PFN for like a kernel. I'm like, whoa, okay. But then you can see down here, this is because I did a dump and there's a realignment again. These are host processes that the diff is realigned. These unaligned ones are in the guest. Also, guest memory doesn't necessarily wipe on the way out. The future is kind of like, okay, well, these weird machines are still happening. This is a tool that Microsoft research guys did. They've got access to the source. They've got a lot more metadata than we do. What that means is, maybe we can use public symbols to the rescue. Sort of. RTTI. There's a lot of anti-ROP attacks that we can then leverage. An anti-ROP attack thing kind of needs to understand the stack and be able to analyze return addresses and make sure they're pointing at the appropriate place, which is also totally possible. So anyone doing ROPs, ROPs are so easily detected. It's not even funny. In summary, there are some issues possibly with GPU. I'm not so sure the EFI stuff is going to work that well from a guest. And then again, finally, we've got this defensive kind of active protection system that you could also try and use, which combines this process detection with integrity checking. There's a link on there. We call it Block Watch or the Memory Cruncher. Let's hear it for the D.
Thanks.
There's a couple more slides. I'm just going to kind of blow through. Use the hypervisor, please. Blue pill, it's not really a problem. Self-map detection. There is one possible thing. If you have a no paging process, that means that the MMU is not involved in that process. There could be something there. So if you're going to rewrite your rootkits to be a no paging rootkit, I'd like to see that. Remote DMA, please no. These network cards with this remote, InfiniBand and everything. Oh man, just don't expose that stuff. Oh, attention Wikipedia authors, editors, anywhere in here. There's actually a page on DCOM and they talk about how this is like very difficult and stuff like this. I'd like to see pre-DEFCON 22, very hard. Post-DEFCON 22, easy. So, DCOM went from very hard, difficult to very easy to detect in one day. So if anyone has any questions or anything, feel free to grab me after. I'm going to show you something, just some eye candy maybe. This is our tool that we have. This is the TDL rootkit. This is our analysis tool. It's free. You can go ahead and download it, whatever. This is a pre-Windows 8, so the kernel executable space. Like, I don't fail closed, and I don't lie about what's executable in memory. I'm not going to hide things from you. Oh, here's the PFN database. It's executable. Here's different processes. This little red bit here is modified, things like that. But if you want to play with it, help us evolve our detection mechanisms, help us evolve the defensive side of things, I'm very confident that there's not going to be a rootkit problem if you're using a hypervisor. If you've procedurally developed your systems, you don't let people execute on your host into your EFI. I'm pretty confident that you're safe. So anything else? That's pretty much it. And thanks for coming. And yeah, it's the death of the rootkit.
Yeah!
We did it!
We finally did it! Yes!